To show you a few examples on how to calculate a normal distribution and some of the steps that are required in order to be successful election. The population support is evenly divided between the two. Both have 50% support. We poll 600 people at random from the population and define a random variable x to count the number of people out of the 600 from our poll that support candidate A. Let's continue here. The distribution from such a poll would be approximately normal. And we'll see that in later classes that that's going to be the case. Close enough that we would use the techniques found in section 1.3 to calculate probabilities, or as we've been doing in 1.3, calculating relative frequencies or proportions. The mean mu of the distribution is set 300 with a standard deviation of 12. Both of these symbols signify that these are not statistics but parameters. Mu is a parameter, it's the exact average, and sigma is also signifies a parameter, meaning that this is the exact value. The difference between an exact value, which is a parameter, and the statistics come from, well, samples. These parameters come from sampling, but the entire population. No element is left out. So here's question 1. What percentage of the time would we have a count of 318 or more from our poll supporting candidate A? Again, I'm going to assume that the distribution is normal. In doing these problems, it's really important to draw a normal distribution. A lot of students don't do this, and this is one of the reasons that they do not do well later on. It's that they don't use the pictures to guide them. You're going to use the pictures to guide you. So I'm going to draw a normal curve. Again, doesn't have to be pretty, just that shape, basic shape. And there, I've drawn one. Now, here's the only thing really we need to fill in order for us to use this. Now, what I need to write is the location of the mean. So it's right here. So I'll write 300. If you saw what I'm using to write this, you would understand why it's so jittery. The next thing I need to write is the location of the value I want. I want a count of 318 or more. So of course, I need to go to the right because I'm increasing. So I don't really care where I put it as long as it's to the right of 300. Again, all I want the picture for is direction. So I'll draw a mark right here. Let's say that's 318. So again, it's probably not the location of 318, but all I care about is, am I to the right or to the left of the 300? And my numbers are deteriorating, but what can you do? And now I concentrate on what I want. I want a count of 300 or more. The key here is or more. So the numbers I'm interested in are sitting to the right of 318, right over here. So in other words, the area above will signify the frequency of getting numbers that are above 318. I'm going to label the axis x because this is the random variable x. And now it says use function notation to represent the question and your answer. So I'm going to come over here and I'm going to write this out using function notation. This is, as we're going to find later on, P is for proportion, or sorry, probability. But proportion works as well for us right now. That this random variable x turns out to be greater than 318. Now, I know you're saying, well, or equal to, so I should put an equal for right now. We'll, in chapter 4, get into more of this distinction. The output from this function will give me the proportion, what I'm looking for. But of course, this is a normal curve. The area represents the proportion, but I don't know how to calculate the area of this. So what I need to use is some kind of software or a table that will allow me to find out what this area is. So I'm going to turn my 318 into a z-score. So now I'm going to write again the function notation. here's my value 318, but to standardize it to a z-score, I need to subtract from it its mean, which is 300, and then divided by its standard deviation. When I calculate, I get 1.5. So it turns out that 318 is 1.5 standard deviations. And of course, you can see the number is positive. That means you're 1.5 standard deviations to the right of the mean, which of course we can see from the picture. Now the question becomes, how am I going to calculate this particular proportion? And you have two choices right now. One is look at a table. The other one is using software. Here's a standard normal table, as such, that is found in your textbook, the front of your textbook. And again, what I have here is on this column the z-scores. This part only goes from the ones units and the tens units, and if you want more accuracy, you have here the hundredths unit. Now our z-score was 1.5, so 1.50. So our accuracy in the hundreds is 0. I'll look up 1.5, and the proportion that I'm being given is 0.9332. But of course, when you get this number, you got to be careful, because if you look at the picture right above here, you see that the area to the left of 1.5, so this is of course representing any value that you see on this column or row here. If you look at 1.5, it's saying the area to the left of 1.5 is this. But of course, that's not what we want. We want the area to the right of 1.5. But since this is a density curve, the entire area here is 1. So let's look at where we find this value right here, 0.9332 in our drawing. So 0.9332 is this area right here. Again, the area to the left of 318. That's this region right here. And again, it's associated with a z-score of 1.5. So that means this area right here is 1 minus this. So our answer is going to be again 1 minus 0.9332. Now let's look at something else really quick before we abandon this. If I go 1.5 standard deviations to the left of 300, and let's say it's right here, just to be again, it has to be symmetric, so even though my original one is not right, I'm just going to assume that this is located right here. So let's say that I'm now thinking about the z-scores, location of this. What is this area right here to the left of positive, sorry, this is going to be negative 1.5 because we're to the left of the mean. What is this area right here? Again, if I look now at the standard normal table, we have the negative z-scores. You'll notice that I can find negative 1.5, and the associated value, which again is always to the left because this table is always going to the left, area to the left of the number you find, it's 0.0668, which of course is 1 minus 0.9332. So we could have just as easily looked at negative 1.5. But again, this is the reason that we draw a picture. That way we keep our orientation. We know which way we're going. We know what we want. We can already expect what we want to see at the end. And again, you can see what the answer here is. It's 0.0668, which is what we found when we looked at the negative side. Let's do the same calculation, but this time let's use software. If I were using software like Excel, the Excel command is equal to norm s dist. Now my z-score for 318 is 1.5. If I type 1.5, and now if I were to hit return, what would this function give me? The same thing as a table did, the area to the left of 318. So the output would equal 0.9332, and then I have to recognize that that's not what I want. After all, the whole picture is 1, and that little region right there in yellow cannot be 93% of the entire picture. It has to be less than half. So I realize what I want is 1 minus this. One way to get around this is to recognize what you're already going to get out, understand how the software works. And so if I were to type norm s dist, knowing that all I want is this little tiny region right here, if I type negative 1.5, the output from this would be 0.0668. Again, it's good to know how the software works, so therefore you can make the decision of what to type in and make sure you understand what you get back out. And that's one of the reasons that the tables can be helpful even if you have software, is that once you understand how to read the table, when you're first learning how to use software, the table allows you to check for any mistakes when you're using the software.